Welcome to Lyons Township High School, AP Physics. Today we've got an example of a bar, and we'll say it's exactly 1 meter long, so something like this, but we're going to make it out of something a little heavier, maybe out of iron or something like that. And we're going to apply a couple forces to it. The bar is pivoted at its center, so imagine there's a nail or something going right through the center of that bar, and it can spin about that pin. Okay, that's the axis of rotation. And we have two forces acting on the bar at different angles. Now, if I'm holding it vertically, there's also gravity acting downward, and the pivot itself would act upward on the bar. Those two forces we're not going to worry about because they cause no torque, because they have no perpendicular arm. In other words, the distance between those forces and this axis is zero, so they don't cause any torque. But those other two forces, this one down and this one up, they are going to cause torque. And we're going to determine two things. We're going to determine the net torque acting on the bar due to those two forces, and what's the angular acceleration of the bar due to those two forces. And we're going to do that both algebraically, and then we're going to plug in, we have a bunch of numbers down here. But we're going to do this algebraically in terms of the givens, in other words, letters. And we have a lot of letters here. We have the mass of the bar, we have L, we have D1, D2, F1, F2, theta 1, theta 2. So in terms of those things, we're going to determine the net torque on the bar and the angular acceleration of the bar, and then we'll throw some numbers in too to just check and make sure we can do that. The first thing I always look at in a problem like this is I try to figure out are the torques clockwise or counterclockwise. So if I'm holding the bar here and F2 points down, F2 is going to try to spin the bar counterclockwise. Okay. Similarly, if I pull up on this side, F1 is going to try to spin the bar counterclockwise. So both those forces are making counterclockwise torques. So I'll call counterclockwise positive. They're both making clockwise torques. So I'm just going to simply add those two torques together. Now, before you do that, one thing you need to figure out is what part of the force actually causes torque. In other words, for F1, it's got a component of force that points to the right and a component of force that points up. Only the upward component, the part that's perpendicular to the rod, is going to cause a torque. So for both of these, I want to find the perpendicular components of those forces to the rod. Okay, so I'll do that up here. So okay, I'll call that F1 perpendicular, and then F2 perpendicular. Okay. Now for this perpendicular component, that's the same as this leg, this vertical leg of this triangle, which is the opposite leg to this angle. So that's going to be sine. So off to the side here, I'll write F1 perpendicular is simply the magnitude of F1 times sine of theta 1. Okay. F2 is not quite the same. I've given you a kind of a different angle. Here, I want the perpendicular, again, it's a perpendicular component of F2 to the rod. Okay, so there's your right angle. Okay. This component is the adjacent leg to this little triangle. So for theta 2, I'm going to use cosine. So for F2 perpendicular, that's F2 cosine of theta 2. Okay, so there are my two components of force that I need to find the torque. Now torque is R cross F, okay? And I've basically already taken care of the cross part of that. I found the perpendicular components of the forces to the rod. So I don't have to worry about this angle anymore. It's right there, or they're right there. Now I've got two forces causing torque, so torque is going to equal, the net torque is going to equal R1 F1. R1 is simply D1, so I've got D1 times the perpendicular component of F1, so F1 sine theta 1, plus D2 times F2 cosine theta 2. So D2 times F2 times cosine theta 2. So if you're asking for what's the net torque acting on the rod, in terms of just the variables given, that's it. Okay. Now if I want to find the angular acceleration of the rod, I set net torque, so I set all that equal to I alpha. Okay, so just like net force equals ma, net torque equals I alpha. So this line will be the same, so I'm not going to rewrite this. So this is something, if you're in AP Physics 1 at LT, this is something that would be given to you. In AP Physics C, you have to actually know this. The moment of inertia of a bar when it's pivoted at its center is 1/12 ml squared. And that's the bar's relative resistance to changes in its spin. So this equals 1/12 ml squared times alpha. Okay? And so if you were solving for alpha, you would take all this and divide it by that, and you would end up with something like this. You'd have a 12 up here in the numerator, because that's your 1/12. You flip it over, it's 12. You have all that, so you got d1 f1 sine theta 1 plus d2 f2 cosine theta 2 all over ml squared. So that's your angular acceleration of the rod. Now, on a quick note, as the rod begins to accelerate, this way, okay, all parts of the rod have the same angular acceleration. Any solid object, if it's spinning, it all has the same angular velocity and angular acceleration. Different parts of the rod will have different linear accelerations, but they all have the same angular acceleration. The entire rod is moving together. Now, if you wanted a value in that, of course, we can sub in all our values and plug and chug. We can do that real quick here. So we got 12. Again, that came from that 1/12 ml squared. You got a d1, which you got to make that into meters. So that would be 0.3 meters times f1. Here, I'll put this in a big square bracket. Times f1, which is 5, sine of theta 1, which is 50 degrees, plus d2, which is 0.2 meters, f2, which is 8, and cosine of 30 degrees, all over m, which is given as 2, and then L is 1, and u squared. And when I plugged and chugged all that into my calculator, I got 15.2 radians per second squared. So that, at that moment, that is the angular acceleration of the rod. So I hope that was helpful, and I'll pull it back down for you. So again, I hope that was helpful, and thank you very much.